This video is going to be an introduction to amines. Before we get into any of the complex chemistry, let's go back to step one, looking at what types of amines we have. Ammonia would be in a nitrogen with 3 hydrogens, and then depending on how many R groups, that's going to increase the number of connections to carbon. So a primary amine would have 1 connection, secondary 2, and tertiary would have 3. Nomenclature is going to be the same, following the same trends we talked about with other functional groups. Amines are very low priority, but if they're the only functional group there, they're going to be your base. So you're going to change your E from alkanes to an amine. So this first one would be methane or methylamine. Here you would have 2-methyl-1-propanamine. So again, looking at the longest chain that's connected to your nitrogen. Here you have a stereochemistry and a double bond, but amines are still going to be your higher priority, giving you your R-trans 3-pentene 2-amine. So again, looking at what's the longest chain of that's connected to your amine. For secondary and tertiary amines, your largest alkyl substituent is going to be your stem. So N-methyl-ethane-amine, we're going to have our ethane, meaning 2 carbons with our nitrogen attached to it. You'll notice that the N-methyl is referring to the nitrogen with a methyl group on it. If you're a tertiary, you're going to have N, N, and then have your groups. So if it's a dimethyl like this one, dimethyl, you could also do N-methyl-ethyl, but still remember to look at your longest chain where your nitrogen is. There are naming systems where you can use it as a substituent, so you would have dimethylaminopropane. Traditionally, this is a little older system, but if you see something named this way, you should be able to go to the structure. Spectroscopy, if we think about IR, looking at this the spectra, we have primary and secondary amines have this broad peak around the 3200 and 3500 range. A primary amine will show 2 peaks, meaning 1 for each hydrogen. A secondary amine will only show 1 peak. That peak, that large, broad peak you see at around 1600 is also important for amines. It's the NH2 scissoring, so you will see that only in primary amines. If it's tertiary, that will only be in the fingerprint region, so you would need to utilize proton or carbon NMR for identification of that. For NMR, we're going to see very similar patterns to the OH. So a typical NH bond is going to be around 1 to 4, depending on what other functional groups you have. Your alpha protons are going to be in the same range as they would with a carbonyl. What you'll notice here is that your shifts are going to be a little bit lower compared to what we've seen with carbons and carbons next to other functional groups. A little bit de-shielded relative to carbon-oxygen bond, so the electronegativity between where the electrons are being held between carbon and oxygen versus carbon and nitrogen is very different. And you'll notice that also in carbon NMR, that first alpha carbon connected to a nitrogen is going to be a little bit more upfield than it would be if it was an oxygen. Okay, let's talk a little bit about the chemistry of amines. They have both acid and basic properties. Relative to alcohols, they're going to be less acidic and better bases. And if we look at 2 examples where an amine is acting as an acid, meaning it's going to give off that proton, have a negative charge, versus acting as a base, it's going to gain that extra proton, having a positive charge. So in order to deprotonate that amine, in order for it to act as an acid, you end up needing a very strong base. And that structure on the right is actually the formula for LDA, one of the strongest bases we use, because that nitrogen very hindered and wants to pick up that proton. Since amines make better bases, let's think about what could separate different types of amines from stronger or weaker. If you remember your acidity trends, these are going to be the opposite when applying what's going to be a better base. So take a second and try to rank these 4 molecules. Okay, so if you know your acidity trends, you're going to actually reverse them here. So our strongest base would be number 4, 3, 1, and then 2. So you should be saying that what's going to make a strong base is it's going to be an electron donating group. So electron withdrawing groups are going to decrease basicity, so our nitro base number 2 is going to be our weakest. If we have an unsubstituted or only monosubstituted benzene ring, like number 1, that's still going to be a better base than having an withdrawing group. Your trends as far as what's a better donating group or what's a better withdrawing group, which one's stronger, follow the same trends we talked about with benzene substituents. For bases, the effects are going to be strongest in the meta positions, opposite of what we talked about with acidity. As far as hybridization goes for bases, you should be saying that our molecule on the right is going to be more basic because the sp2 carbon is going to be withdrawing, and we just discussed about those being negative for bases. This also follows the trend of hybridization, so your sp3 hybridization amines are going to be your most basic, then sp2, and then your sp. Making amines. Making amines, we're going to go over a couple different ways. One of the most common ways is you can use a cyanide ion, have them replace it with a SN2 reaction with an haloalkane. Then you can use a strong reducing agent, lithium aluminum hydride, or hydrogen to reduce that to your amine. So here's our synthesis. We have our starting with the haloalkane. We can do an SN2 reaction. DMSO is a big indicator that that's going to happen. From there, we can just hydrogenation or any other reducing agent. Now we have our primary amine. If you don't want to add that extra carbon that comes with the nitro group, you can use sodium azide. Same mechanism that nitrogen group's going to add. You can see here we have a great leaving group with our 2 nitrogens on the right-hand side. So we can still reduce that, and you'll notice we have not added an extra carbon, but we've made the same type of functionality as our last reagent, an amino group, primary amine. The Gabriel synthesis is another way where this can happen, where we can add an amine to a system that's going to be restrictive in what can happen to the nitrogen afterwards. So here, if we have a very strong base, we can end up deprotonating that amine and have that act as a nucleophile again onto some sort of R group attached to a bromine, same type of SN2 reaction. We can then kick off that entire group using acid, so we break up that lactone, and then we're left with our amine with whatever R group we have that we added on during step 3, and you have your, based on the conditions, you have that other half of your molecule that's going to be removed because it's charged. Reductive amination is another method where we can create amines. So amines can be added instead of a carbonyl, so that the double bond from the carbon to the oxygen can replace with the nitrogen. This should remind you of chemistry we talked about earlier in the quarter, looking at reducing that. So we'll again reduce that. Our carbon will stay, and we'll have a nitrogen that is now a secondary amine with only 1 hydrogen. Some examples here. So again, our nitrogen is going to take the place of oxygen. Here we only have ammonia, so we're going to still have, we're going to go up in one step. So we'll go from ammonia to a primary amine. We can also go from a primary amine to a secondary amine. This reagent here, the NABH3CN, is another common reducing agent you'll see if you don't want to deal with any of the high pressure or heavily reducing agents, heavily reactive reagents. The last method for making amines we'll discuss in this video is the Hofmann elimination. You can take an amine and exhaustively methylate, so add methyl groups to it, heat it up using base to create an elimination reaction. You now have a good leaving group, and you're left with an alkene and your tertiary amine. This is the Hofmann elimination, the same Hofmann we talked about with least substituted alkene being the Hofmann product. And if you have the option of which ones you're forming, the least substituted alkene will be the one that's formed. In this case, we only had 1 alkene that could form. Let's go through this mechanism. So our first step is going to be an exhaustive methylation Since it's a poor leaving group in the beginning, we need to add methyl groups until it becomes a good leaving group. Once it leaves, we can use silver oxide as a way to help precipitate out silver iodide, make sure it's not a salt anymore. We now have an ammonium hydroxide where our base is already there. Our hydroxide will be used as our elimination reagent, so it'll pull off our hydrogen, drop down to an alkene, and give us our tertiary amine. That's it for the introduction to amines.